Okay, so just a little clarification on molarity and creating something that's 1 molar. So if I say these are my hydrophilic water gels, I have 4 of these, and I'm going to say that 4 of these gels is 1 mole. So I'm going to put these 4 moles in here. I definitely broke one. But so I put these 4 moles in here, and I want a solution. I'm going to fill it up to 50, and we'll say 50 is 1 whole liter. Okay, so if you can zoom in on that, we've got 4 of these in 50 mils, right? So now, I want to fill this up to 50 mils too. Very good. One more. So they're at about the same volume, right? You agree, photographer?
Yes,
okay,
they are.
So I'm going to take the same 4 beads that I'm calling 4 moles and add them in here now. Now the question I would ask is, which one of these is more concentrated? Good.
This one.
Water vapour spreads out into the atmosphere. It's carried by the wind, but it can also spread out of its own accord by a process known as diffusion. Invisible gases behave in the same way. The particles in a gas move randomly in all directions. This helps explain why a gas diffuses from one place to another. You can see diffusion happening on a small scale in the lab, using bromine, an orange-coloured gas. Place a jar of air on top of the bromine, and it slowly starts to spread. It's moving up the tube against gravity. Over time, the 2 gases mix. After half an hour, both containers have a uniform colour. It takes time because the air and the bromine molecules are colliding with themselves and each other. So what would happen if there was no air for the bromine to bump into? All the air has been removed from this apparatus, apart from the flask containing bromine, which is isolated by a tap. Open the tap and it spreads immediately. Watch again. In a vacuum, there's no air to collide with. The bromine diffuses much faster. See how slow the diffusion is when the flask is now full of air. It takes several minutes to get just this far. This simple setup can be used to compare the rate at which different gases diffuse into air. Nitrogen dioxide gas on the left is similar in colour to bromine on the right, but bromine molecules are much heavier. The lighter nitrogen dioxide diffuses more quickly. We can also compare the diffusion rates of other gases. Ammonia and hydrogen chloride gas are colourless, but when they meet, a white cloud of ammonium chloride forms.
Okay, so here we have Miss Molly and Miss Liz, my TAs for the day. We're going to demonstrate how to set up the lab called Race of the Gases, okay? So Molly has a Q-tip and some really concentrated hydrochloric acid. And Liz has some really concentrated ammonia and a Q-tip. So what they're going to do, they're each going to take their Q-tip and saturate it with their respective liquid. Okay? Then we'll show Liz first, slowly inserting the Q-tip into the tube until it's covered by the tape, and then placing a wet paper towel sealed around it. Now Molly does the same thing on her side. Now, what's the wet paper towel for? You guys know?
To keep the gas going that way rather than that way.
Yes, we don't want the gas to escape. So right now, these liquids are producing gases that are racing to the center of this tube. And what you guys are going to do in this lab is watch for that to happen. And the other thing, you guys will get a procedure for this, so you'll know that you're supposed to be timing this to see when these gases meet, because when they meet, they're going to form something. Now, what do you guys think it might form? What?
Precipitate.
Yes.
Mr. Sams?
Yep.
Like, what are you doing?
Playing with the syringe.
A syringe? Like,
Yeah.
do you have like a drug problem? Or what
No,
are you doing
I
with a
don't have a
syringe?
problem. Just playing with it, because you can learn a lot about gases from just playing with the syringe. See, look at this. See, there's nothing in here, right? Little tiny bit of gas.
Yeah, yeah.
Okay, I pull this out, and the pressure is really, really low in there. You know how I know it's low?
I don't know.
Because the atmosphere pushes it back in. when it's
Very
low.
cool,
Isn't that
Mr.
neat?
Sams.
Yeah.
You're like a Tinkerband.
And I can push this down, but I can't push it all the way down because I
Really?
can only compress it so far. And then,
Oh.
see, I let
Yeah,
all the
you let
pressure
gas
Here,
out.
I'm going to let it push.
Oh, should we do it again? All right, let me
Well, I'm
zoom
going to
in.
let it push the plunger back at itself.
Oh, nice.
Or you can just, let it go there. But yeah, you can learn a lot about cool things about volume and pressure with gases and just playing around with the syringe. So I just like to fidget with things and play with stuff.
Okay.
You know,
So
I'm
what are we
kinda-
going to talk about today?
Kind of wiggly. We're going to talk about gases and how they work in terms of pressure and volume and temperature and things like that.
Cool.
What is kinetic energy? So why don't the gases attract or repel each other?
What's velocity?
What's an ideal gas?
Why do the particles move at different speeds?
Is their movement random?
How does the gas equation work?
And now another one together. What is PivNert?
Pivnert?
What the heck is PivNert?